We have that important statement whereby we are saying that the boundary of a subset of topological space T, the boundary of a subset of a topological space T, the boundary is empty if and only if H is open, close, and open at the same time. So how can we prove this? How can we prove this? So we are going to suppose if and only if statement. So suppose that the boundary of H is empty. So we show that H is open, closed and open. So what are we going to show? We show that in particular the closure of H is equal to H. That implies that H is closed. We show that closure of H is H, then H is closed. Also, we show that the interior of H is H. That implies that H is open. Now we know that the closure of set A is equal to closure of set H. Closure of set H is equal to the interior of H union the boundary of H. We are saying that boundary of H is an open set, so we have the closure of H equal to the interior of H union an empty set. So the closure of H is equal to the interior of H. Closure of H is equal to, think about that statement, closure of H is the same as the interior of H. What comes to your mind? So we know that A is a subset of H is a subset of H is a subset of closure of H. H is a subset of closure of H, and also the interior of H is in H. So we know that statement. H is a subset of the closure, and the interior is a subset of H. So we are saying that but closure of H is equal to the interior of H. So if closure of H is try to substitute, we shall have interior subset of H. So where there is this, I'm going to put interior because the closure is equal to the interior. So this implies that H is a subset of the interior. Also the interior is a subset of H. So this alone implies that H is equal to the interior of H. Similarly, if we substitute where there is interior, we put closure of H, subset of H, subset of. So we have H being a subset of the closure of H, and also the closure of H being a subset of H. This implies that H is actually equal to closure of H. So H is clopen. H is closed and open. Then conversely, the spelling, you try to check the spelling, it's not somehow fine. So conversely, we suppose that H is open. So H is closed and open. H being closed, H closed implies that the closure of H is equal to H. H open implies that H often implies what? It implies that its complement is actually closed. So the complement of this, which is equal to T minus H is closed. Is closed, i.e. T minus H closure is equal to T minus H is equal to T minus H. Now we can proceed. We want to show that the boundary is empty. We want to show that the boundary is an empty set. We want to prove that the boundary is nothing else but an empty set. So by definition, we know that the boundary of H is equal to what? The boundary of H is equal to H closure intersection T minus H closure. So the closure of H is H. Closure of H is H. Intersection closure of T minus H is T minus H. So we have the intersection of H and its complement, and this is an empty set. So we are done. We are done by that way. Yeah.